Hi, I'm Michael Pallas. I'm an associate professor in the Department of Earth Sciences at the University of New Hampshire. And my involvement with the eMERGE Institute is remote sensing, specifically looking at drones with high spatial resolution and also high hyperspectral resolution or spectral resolution to kind of integrate some aspects of these projects or these different kind of groups, research agendas. So I'm going to summarize a little bit about remote sensing. My goal is to, no matter what your discipline is, make you comfortable with some of the remote sensing terms, platforms, and concepts, and make sure that you can use remote sensing in the future, possibly for your work, or work well with remote people that do remote sensing. So consider it a tool, much like GIS is a tool to answer some questions specific for your discipline, or it can be considered a discipline into itself. And I do a little bit of both. Some of the stuff I work on is very technical, LiDAR oriented, which is a laser range finding remote sensing technique. And then some of it is really just providing data sets for other disciplines in science. So looks like my battery is starting to go. So I am going to pause my recording and then I'll start right back in a second. Okay, I'm back. We should be recording. So I'm going to talk a little bit about remote sensing and tell you some backgrounds. Here's a picture of Frankie Sullivan, who's part of our group, flying one of our drones in northern Canada and collecting some data on some fens and pulses there. So what is remote sensing? Remote sensing really is using some sort of instrument to remotely detect things. Now, in some ways, you can consider that if you're using a GC, you're actually remotely sensing the gases. But really, we look at the kind of structures or features on landscapes or an object, and often it's related to light. So there's a lot of electromagnetic radiation. We as humans focus in on what we can see as part of visible light. And these are important aspects in how we kind of perceive the world. So we're actually pretty good remote sensing devices ourselves. So remote sensing is the acquisition of data remotely. Often it's called Earth observation or remote sensing, so EOS. And there's many different instruments and platforms. The instruments are called sensors. The platforms are the things that carry these things. So an instrument could be just a normal camera that you have. A platform could be an aircraft, a helicopter, or a satellite. And so we'll look at some of these in relation to work that could answer some questions on vegetation. So it sounds kind of simple that what we see is what's there, but really, if you've ever driven in the hazy, Washington, D.C. area, you know that wearing polarized sunglasses really allows you to see things a little better. And that's because light takes a lot of different pathways from the sun to you. There's 4 different pathways that that light could take. The one that we like the best with the clearest route is number 1 here, which goes right through the atmosphere, not disturbed by the gases in the atmosphere or water droplets. It hits the object and bounces right to us, which is the observer here. Sometimes light hits something else and gets scattered through the atmosphere and through additional atmosphere as it goes off the object. Some things do secondary hits. So it's a really complicated science, but really we want the clearest, cleanest data that's coming directly from that object. So remote sensing has a long history. So as soon as cameras were developed, people wanted to take pictures from the air to perceive things differently. So people originally started to put little cameras up on pigeons and birds, put them up on kites and balloons. One of the first aerial photographs, it was here on a street in Paris. And you can see, if you zoom in, you can see that there are people down here meeting up. Maybe someone's shining a shoe, or it's a couple meeting. But it's exciting. We can see these things from the air. Some first aerial photograph was actually taken by a kite over part of France. And these images were also collected after the earthquake and fire in San Francisco. And so this was taken from a kite in 1906. And you can see many of the blocks of the city burnt down. The interest has also been in military. So having information behind enemy lines, be it a balloon during the Civil War, where the person could see across the field, to early US satellites that tried to collect data on the Soviet Union. So there were a series in the 1960s of satellites called Corona that collected that imagery. Now, what's really interesting is this was really before digital cameras. So what the sensor would do is it would take a picture, it would turn 120 degrees, it would thrust a small cone out, that cone would separate, it would have a parachute and a small, with the film, the physical film, and then there would be an aircraft down there that would actually recover the film before it hit the ocean. And so here's a picture of one of those aircraft collecting that data. We also look at U-2 spy planes or this Black Hawk. These were interesting. These were super, super fast, one of the fastest airplanes ever developed. And so there were two ways to do it. You could go really fast over enemy territory and take pictures, or you could go really slow and high like the U-2 spy plane and take imagery. This U-2 spy plane has actually been converted into a NASA data collection. So the sensor is a hyperspectral camera called Avarice, and it is flown on the U-2 spy plane for science now. So these early images were kind of what we call RGB imagery. It was collecting, but there's a lot of other different electromagnetic radiation out there, and we can often use these to understand features on the planet. I'll go into these a little bit in this lecture, but if you had a full remote sensing class, you'd start to learn a little more about radar and a little bit more about LIDAR. So if we look at the electromagnetic spectrum, you can see that the visible light is just down here. This is sunlight as it comes in, and this is what we see. And this is cute because you can see that things that have a slower wavelength, like the wave in a stadium or slinkies, have a slower wavelength, as we say. And as things get higher, they have higher wavelengths. So it's really kind of a neat way to look at the kind of spectral imagery. So some cameras can collect the full spectrum. So this is going from right here. This is blue. This little bump is green. That's the green light being reflected by the plants. Red. And then we get into here. This is the near infrared. And this is highly reflected by plants. Plants don't really use this energy and reflects a lot. And then you go out into these kind of higher wavelengths, and you're getting really into kind of what we call the shortwave infrared. And this is often where kind of some nutrients of the plants or water content of the plants can be teased out. You can also use the spectral signature to tease out different species of vegetation. So here we have some species from the tropics, Cecropia, one of them, and you can see that they have different reflective responses to the light, and that can tell you what plants you're seeing. So two terms in remote sensing that are really important: resolution, which is an indication of how dense or what kind of features you can see spatially; the quality, the frequency, and then also the spatial area. Correction is another one. It's often not really considered because many people use cleaned up products or corrected products. And so it is an aspect of remote sensing to kind of increase the accuracy. So if you have an image in a cloudy day or when there's haze, that's not going to be the true kind of response or what the vegetation would emit on a clear day. So you need to correct that and make them similar. Just to show a little bit about spatial resolution, this is an image from a satellite called Worldview 2. This has about a 2-meter multi-color resolution. If you just looked at black and white, which is grayscale, it would be a 0.5 meter. So this is the Taj Mahal. So you can really see some interesting features teased out there. This is the Superdome after Hurricane Katrina. You can see that some of the tiles were blown off from the Superdome, and also that the streets tended to be flooded here. Here's a volcano. You can see the small kind of channels running off the volcano. You can also, this is the reason why the vegetation is red here, is we're actually using the near infrared in the red band. The red goes to green and the green goes to the blue as we see it. So this is called a false color composite. And it's a good indication of vegetation characteristics. What's interesting here is you can see that this is a California forest fire as it's starting to encroach or move across the landscape. So features such as, this is the Greek Summer Olympics. I thought that'd be important since we have the Summer Olympics going on in Tokyo. As you zoom in, you can see features, and specifically you can see features, though that they're small. If they're linear, they're easy to tease out. So when we look at some of these images of Stordahl and Meyer, you're going to actually see that you can see the boardwalks where scientists walk to work as features that are easier to see than maybe a small patch of vegetation. There are also satellites that collect with lower resolution, but collect vast areas. So once again, if we looked at the Worldview 2 image of the Taj Mahal, it's really just focusing maybe on a 5 by 5 kilometer area. Here, this is taken by the Terra satellite. It's part of the Modus constellation. There's Terra and Aqua. Each of these satellites fly over the planet once a day where it's light and image the whole planet. So here we actually have collected 8 days of data, teased out the clouds, and we're able to get a full vegetation or enhanced vegetation index of the entire continent of South America. This is something you could not do with airplanes or drones, and even higher resolution satellites couldn't do that. So MODIS's kind of advantage is, though coarse resolution, usually a pixel is about 500 meters, it can tell you a lot about everything temporally. And MODIS has been collecting this data for about 20 years. So let's talk a little more about resolution. So if we talk about spatial resolution, it's really how small those pixels are. Landsat is about 30 meters. MODIS we talked about is at 250 meters to a kilometer. And that Worldview 2 that we looked at earlier was about 50 centimeters. Also, things have changed over time. Sensors have gotten more sensitive. So early, what we term Landsat from the 1970s and 80s had values only ranging from 0 to 63. Landsat, the newer Landsat has it going from 0 to 255, and even newer Landsat has improved on that more. Landsat 8 is the most current one, soon to be launching Landsat 9. Iconos, which is that kind of high resolution spatial, also has a really sensitive sensor that's on, you can get values or small discrete aspects of the light bouncing off an object between 0 and about 8,000. So let's look at Stordahl and Meyer, Abisko, Sweden. Here it is up in the north. You guys have probably already talked about it as part of this Emerge Institute. But we're interested in kind of the higher spatial resolution just at Stordahl and Meyer. So if we look at MODIS, this is a picture of MODIS collected. So this is 1 to 2 times temporal resolution, so 1 to 2 times per day. It has 36 bands. So it doesn't just have red, green, and blue, but it also has near infrared, different near infrareds, shortwave infrared. It also collects kind of the higher than blue to look at aerosol concentrations in the air. But really 19 of these bands allow you to look at vegetation. If we zoom in at Stordahl and Meyer, it looks a little bit like a Minecraft world. We still have about a 500 meter resolution. Here you can see the large lake. Here you can see some sort of vegetation differences that are along the Meyer. Here's a larger lake. If we zoom into a Worldview 2 image, you can see that only this really big lake was indicative of water body. This was the Meyer that we were looking at that had those different kind of colors. This is that road coming from Kiruna, as well as the railroad. If we zoom in a little more, we can actually start to see the features of that boardwalk as the scientists kind of make their little ant trails across the landscape. And Worldview 2 is about 0.5 to 2 meter resolution. You actually have to task the satellite that says, please take a satellite here, and then you have to pay for it to get that information. If we zoom in really close, this is kind of the instrument shack at Stordahl, which Ruth might have talked a little bit about. So this is an instrument shack. You can see the boardwalk there, and it's pretty pixelated because each of these pixels is about a half a meter. And this is where drones come in. So a drone of that area would actually see even the difference between the two planks on the boardwalk. And you can see really distinct features of the vegetation. And you can start to see smaller pulses and thaw ponds. And so this is really helps to get an idea of the landscape. So if we look here, we can actually see some of the auto chambers here. And that's about 40 centimeters by 40 centimeters. So it really starts to get into understanding the landscape. So as a scientist, you need to understand the spatial resolution and also the temporal resolution. How often does this satellite collect? MODIS has been collecting for 20 years. We at Stordal and Myers have collected imagery for about 7 years, but only one image per year. MODIS has that every day. Landsat takes about every 14 days. And it's been going, different flavors of Landsat have been going since the 1970s. So if you're looking at species mapping, you might just need a really high resolution once a decade or once a year. If you're looking at fire, large scale fires, you might need daily information with a coarser resolution of 1 kilometer. So these are trade-offs. You can't have everything with remote sensing. And so this was work that we did looking at tropical questions that